Okay, to make things more clear, let's actually solve an example. So in this example, the question is telling us that for the circuit shown below, determine the relationship between RC and VCC that guarantees operation in active region. Okay, I know that to be in the active region, my VCE, or let's actually write it, to be in active region, VCE has to be greater than 0.2, right? I'm not talking about shallow saturation or anything. I'm talking about like going to deep saturation. So I'm just trying to avoid that, right? So I want to make sure that I still can basically use my exponential equation for the collector current and base emitter voltage and all that. And I can still use my beta to relate the collector and base current and base and emitter current and such, right? So I know that I want VC to be greater than 0.2. So now how VC is related to RC and VCC? Well, I know that this is the collector voltage and this is the emitter voltage. And the difference is VCE. So VCE is equal to VC minus VE is equal to VC minus 0 because emitter is connected to ground, right? Now, how can I write VC based on VCC and RC? Well, VC is actually VCC minus RC times IC, okay? Just use the KVL. Now, this tells me that I need to make sure that VCC minus RCIC is always greater than 0.2 volts to make sure that I'm in the active region, okay? So remember that, just want to actually remind you of something very interesting. Remember that when I was actually talking about the biasing of transistors and this exponential thing that was relating VBE, the base emitter voltage, and the collector current, and when we were talking about GM, and I was saying that I always want to be in a point, I want my operating point of, or the point of operation to be at a certain part of this curve that has a higher slope, right? Because I know that the more I increase VBE, I'm going to have a better slope. Therefore, I'm going to have a better GM, right? Because my GM turned out to be IC over VT. So the bigger IC, the bigger GM. And remember that I said there's a trade-off that, well, why don't I just increase my VBE to infinity and enjoy my really high gain of transistor? Well, because that meant that current of the collector is going to be increasing, therefore I'm going to have more and more power consumption, right? There's actually another reason that I don't want to increase VPE, and there's another reason basically against increasing GM without any kind of limitations, and that's really here. If I increase IC, even if I don't care about power, looking at this expression, I can see that, well, my VCC is the supply voltage, so that's a constant value, right? RC is a resistor, that's also constant. IC, if I increase IC, what happens is that this expression is going to result in a smaller and smaller voltage. Let's say that if VCC was like, I don't know, 5 volts, and RC was 1 kilo, right? Now, if IC was 1 milliamp, then I was fine, because 5 minus 1 kilo ohm times 1 milliamp, that's 4 volts. Because 1 times kilo times milli, they cancel out. This becomes 1 volt, 5 minus 1, 4 volts, I'm good. If I make the 1 milliamp, if I increase it to 2 milliamps, I'm still good. 5 minus 2, 3 volts. But if I increase it to 5 milliamps, 5 minus 5, 0, I'm not in active region anymore. So another reason for me that I don't want to go too far in this curve and go to these kind of like points of operation, and I want to stay within, I don't know, 0.7 to 0.75 or 0.8 kind of region, is simply because not only it increases the power consumption, but also even if I don't care about power consumption, I might actually risk my transistor going to the saturation region, or in other words, becoming useless, right? Not actually having any kind of amplification because it's not a transistor anymore. We saw that it's not really a voltage controlled current source anymore. Okay, you might wonder, well, what will happen to, I can still increase this current. You might, if you actually are very curious, you might say that, well, I can still increase this current and decrease the resistor, and that the multiplication becomes, well, I can keep the multiplication constant, therefore I'm going to avoid going to the saturation region. And that's actually correct. You're not going to go to the saturation region. You still have the power problem, but later on you will see that you're not going to get a better gain out of this transistor, because if you go back and calculate and look at the example that we calculated the gain, you will see that the gain of this transistor is actually GM, the multiplication of GM times RC. And there's a negative involved as well, by the way. This is all of the things that I'm talking about here from this point forward is in this slide is just basically something that I'm going to discuss in the next chapter. I'm just giving you a little bit of a sneak peek, right? So the gain, if gain is actually GMRC, yes, you can still decrease RC and avoid saturation, but then, and you're going to increase IC and get a better GM, but at the same time you're decreasing RC. So at the end of the day, your GM is increasing, but with the same ratio, your RC is decreasing. Therefore, your gain becomes constant. So you don't have any kind of advantage in terms of the voltage gain of the amplifier. Okay, you just basically increase the power for no reason. We are going to discuss this a lot more in details in the next chapter. So let me actually erase all these stuff. But not going to saturation is one of the biggest reasons that you don't want to actually increase the current, the collector current of your transistor. So based on the discussions of this slide, we can see that if I want to make sure that I don't go to saturation, I have to make sure that I set my base emitter voltage, because the base emitter voltage is what sets the collector current, right? Because I know that if I'm in the active region, IC is IS exponential of VBE over VT. Okay, so if I want to make sure that I don't go to saturation region, for a fixed RC and a fixed VCC, if I want to set IC, then I have to set VBE in a way that, well, VCC minus RCIC is greater than 0.2 volts. If the IC and VBE are actually fixed, then I have to change my VCC and RC in a way that at the end of the day, the VCC minus RCIC is greater than 0.2 volts. Okay? And by the way, this is not a golden expression or anything. It's not that like always we only look at VCC minus RCIC. This is only for this circuit. So if I give you another circuit, you have to find VCE and make sure that VCE is greater than 0.2, right? In this case, VCE was, well, it's always VC minus VE, but in this case, emitter was actually 0. In other circuits, it might not be, and collector was VCC minus RCIC. In other cases, collector voltage might be actually have a different expression, right? But the most important thing is that you always have to find the collector emitter voltage to find basically to figure out if it is bigger than 0.2 or not. If it is bigger, you're good. You're safe. You're in the active region, and everything is good. If it's not, then the active region assumption is wrong. Your transistor is in saturation region unless you find a way to actually bring it out of saturation, meaning that either making IC smaller or RC smaller or VCC larger.